So welcome everyone for the this mini course on Markov Chains by Professor Manjunath Krishnapur. He will deliver his lecture, third lecture for 1 hour. Then 11:30 we will have a small break, and we'll resume from 12 to 1. So please put your comments in the Q&A chat box, as well as those who are watching on YouTube can comment there. We will ask the question to Professor Manjunath. Hand over to you.
Oh, thank you. Thanks again, and thanks to everyone for coming on Sunday. Yeah, so I will continue where I left off last time. So main thing is the long-term behavior of. So let me recap what it was. So very quickly. So what we saw was by some examples, we saw that in many cases we have this transition matrix. So Markov chain has a finite state space for us and a transition matrix which is n cross n. And then what we main point one calculation we did was if I want to know what happens after n steps or after t steps. So what is the probability that if you start at I naught, after t steps it is at j, that is same as you raise the matrix p to the power t, that is you multiply the matrix p t times and then take the I naught comma j entry. So everything depends. So if I want to know long term, what is the probabilities with which after a long time, where will the Markov chain be with what probabilities? Everything depends on knowing the powers of p. And then what we did was in some simulations here, we did a few simulations with, simulations or numericals, where we saw that when we raise a transition matrix to a large power, quite often it looks like all the rows become equal. And we discussed what the meaning of that is. It means that if p to the t converges to some matrix like this, so this is what we are hoping for behavior, p to the t converges to entry by entry, it converges to this, as t goes to infinity, converges to a matrix Q, all of the rows being the same. And I'm calling it pi 1, pi 2, pi n. That means that p to the t I comma j, that is the probability to be in j at time t when you start at I at time 0, is approximately pi j after for large t. So it forgets where it started. Wherever you start, you will end up at j. So this we have not proved. This is something we observed. Okay. And what we saw is also that it's not universally true. We saw two examples where this type of behavior is not valid. So it is something we need to figure out when we can make this conclusion. This is just an observation so far. And now also we did another thing for two-state Markov chain. If we take this where alpha and beta are strictly between 0 and 1, then we showed that this is indeed true. That is a very special case of two-state Markov chain, that this kind of behavior is true. We showed that if you take p to be this and alpha beta have to be strictly between 0 and 1, then p to the t converges to this matrix beta over alpha plus beta, alpha over alpha. So pi 1 will be beta over alpha plus beta, pi 2 will be alpha over alpha plus beta. Those will be the probabilities. In other words, if we have a chain like this, it doesn't matter where you start, after a very long time, you are likely to be in state 1 with probability close to beta over alpha plus beta, and in state 2 with probability alpha over alpha plus beta. So this is what we have solved. And now we have to go to the general situation and see how we can answer this question. Now, the trick that we used in the 2 by 2 case was to diagonalize. So let's first start there. Maybe if P is diagonalizable, then we can certainly try the same thing. Okay, so let me write the problem. So the problem is so the issue is, what we want to do is goal, figure out when p to the t converges to some matrix which I'll call Q, which is of the form pi 1 up to pi n, and all the rows are the same. Okay. Someone asked if this has a name. I did not have any name, but it is just a rank 1 stochastic matrix. In fact, any rank 1 stochastic matrix has to look like this. Pi i's are greater than equal to 0 and summation pi I So this is a rank 1 stochastic matrix. So this is what we want to do. So first case 1, simple case, or maybe simpler case, I don't know, whatever. Simple, the easier case, I should have written, is when suppose we assume that P is in fact, so assume that P is diagonalizable. I'm making this assumption. P is okay. Maybe even before going to that, I have to tell you a couple of things about a general. Maybe I write it since I started and I will explain later. Diagonalizable and has eigenvalues. So lambda 1. So one of the eigenvalues of P is always 1. This is what I will explain. And then there are some other eigenvalues, lambda n, with mod lambda k strictly smaller than 1 for all k greater than equal to 2. So one eigenvalue, so let me, maybe I go there and I should have started there, just escaped my mind. So let's do some preliminary study of, so two facts about, so basic observations. So let P be any stochastic matrix. That means a transition matrix. Fact 1 is an eigenvalue. Why is that? We know that the row sums are 1. So that means if I multiply P by the vector 1, 1, all 1 vector, what do I get? When I multiply P by this, first entry will be first row multiplied by this, which means the first row sum. So what I get are the row sums, but I know that the row sums are 1, 1, 1, 1, 1. So this is why, so this vector, if I call this vector as the bold 1, so P applied to this vector gives the vector back. So 1 is an eigenvalue. And this is at least one eigenvector for that eigenvalue. Okay, there may be, it may happen that an eigenvalue occurs with greater multiplicity. That will be the source of our troubles. But at least one is certainly an eigenvalue, and this is an eigenvector. Second statement is all eigenvalues are of all eigenvalues any eigenvalue, let's call it lambda of P, satisfies mod lambda is less than equal to 1. There cannot be any eigenvalue which is strictly larger than 1 in absolute value. Now remember that even though the matrix may have real entries, the eigenvalues may be complex numbers. So here it's a complex number, but the complex number has absolute value at most 1. So why is this? This is a simple enough thing. Maybe you would have seen this in some this kind of reasoning in some linear algebra class. But so the reason is, so okay, so you take any, so what is the meaning? So suppose PV equal to lambda V. Okay. So what does that mean? That means lambda times Vk is equal to PV kth entry. But what is the kth entry of PV? It is P, we take the kth row of P and multiply the vector V. So Pkj, Vj summed over J in S. Okay. So this is for all k. For all k in S, this is true. Now let's take absolute values on this. If we put absolute values on this, so we'll get mod lambda times mod Vk is less than equal to, and I put the absolute values inside by triangle inequality. Since pkj are positive, I don't need to put an absolute value around that. Pkj mod Vj. Okay. Now we can certainly bound this. Let's replace this by the maximum of these numbers. Okay. So what I will do is I will replace all the Vj's by the maximum over j of mod Vj. So if I replace each of this by the maximum of those, then I can pull that out, and what I am left with is sum, row sum, which is 1. Right? So, but now you take k to be exactly the one that with the maximum, which achieves that maximum. Okay, if you take k to be the one that achieves the maximum, you see that lambda has to be less than equal to 1. Or to put it another way, this is true for every k. Mod lambda mod Vk is less than equal to this for all k. Take maximum over k, you'll get that mod lambda times this maximum is less than equal to the maximum, which means mod lambda is less than equal to 1. So any stochastic matrix has all its eigenvalues in the closed unit disk in the complex plane, and one of the eigenvalues is certainly 1. What is extra I am assuming here is that one is that P is diagonalizable. That is absolutely by no means in general true. P is diagonalizable, that I am assuming. Secondly, I am assuming that, okay, one eigenvalue is 1. I'll take that to be, I can arrange the eigenvalues as I want. So this is not an assumption. Okay, so this is not an assumption. So the first eigenvalue I'll put, but what I'm assuming is there is first of all, this eigenvalue 1 occurs with only multiplicity 1. Okay, so it occurs with multiplicity 1, and also all the other eigenvalues which have mod lambda less than equal to 1, I'm assuming it's actually strictly less than 1. So that is the extra bit I'm assuming here. So this strict inequality of all eigenvalues. So in other words, one eigenvalue is 1, all the others are strictly less than 1. So that's how I am assuming. So diagonalizability and this. So if we assume this, then problem is easy. So the problem becomes easy. How? We will do it now. So if this is the case, then we can write P as x d x inverse. That's the assumption of diagonalizability, right? I mean, you can write there's a full basis of eigenvectors. The columns of x are the eigenvectors of P, really. So first, let me write this. So D consists of the eigenvalues. We can order them like this: 1, lambda 2, lambda n. So let's order it like that. So what will be the columns of x? The columns of x will consist of eigenvectors of P. Okay. So what will be the first column then? That will be the eigenvector corresponding to 1. And since this is the eigenvector corresponding, there one is a simple eigenvalue. So there is only one. This x1 first entry, first column is 1 1 1 1 1, and then whatever is there is there. Okay. And x inverse, I don't know anything about it, but let's write x inverse just for a moment. Let's write it as first row, let's call it pi 1, pi 2, pi n. I'm not saying anything about this as of now. It's just a symbol. Okay. The first row of x inverse, I call it pi 1, pi 2, pi n. Okay. All I have done is I have written the assumptions in this mathematical notation. So, but if we have this, what happens to p raised to the power t? This is the trick we saw last time, that when we take diagonalize and then take powers, all this x inverse x cancels. So we get x times d raised to the power t x inverse. Okay. And what is d raised to the power t? it will be 1 lambda 2 to the power t, lambda 3 to the power t, lambda n to the power t. Okay, so this is x times 1 lambda 2 to the power t all the way up to lambda n to the power t, and everything here is 0. This is the diagonal matrix. And then I have x inverse. Now what happens to this as t goes to infinity? As I let t go to infinity, this will be all these lambda 2 to lambda n I have assumed have absolute value strictly less than 1. Okay, that's an assumption. Just so that now all of these will go to 0. Right, so that assumption was made so that I get here as t goes to infinity, 1 and everything else is 0. Off diagonals are 0, even the other diagonals are 0, and x inverse. Okay, so we get a very simple matrix in the limit. P to the t converges to this matrix. But what is this matrix? If you multiply it out, it is very easy to see. You just multiply, you will just get, I will leave this as short exercise. If you don't see it immediately, just do it. X is x first column I have written, x inverse first row I have written, and nothing else matters to do this because most of the entries are 0. It doesn't matter what else is there in x and x inverse. What you just get is pi 1 dot 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 pi n. Each of the rows will be converging to, will be equal to pi 1 to pi n, etc. All of them are the same. And this is the conclusion I wanted to get. Okay. So in other words, we are getting that p to the t, if I take I comma j entry, that converges to pi j for all I comma j in S. So from that we also see that since p to the t, the p is a stochastic matrix, and we saw p to the t is also a stochastic matrix. So all the entries are non-negative here and add up to 1. Row sums are 1. Therefore, pi j will also be greater than equal to 0. Non-negative things can't converge to something negative. So pi j will be anyway greater than equal to 0. And sum of pi j will be equal to 1. Okay, so this is what happens. Okay, this is because p to the t ij are greater than equal to 0. And if I sum over j of this, then I get 1 for any I. So that is why the limit also, the row sums will be 1. So this is the final conclusion we wanted. So if we assume that P is diagonalizable and has eigenvalues like this, then everything is good and what we wanted is true. But except that this is a bit restrictive. Okay. Okay. Are there any questions at this point? Then I will go to the more general case where how to maybe decrease the restriction. This was where the diagonalization allowed us to solve the problem completely. What if it's not necessarily diagonalizable? What can we do in such a situation? Okay, so that's what I go to next. More general case, maybe I write here. So it's more general. It's never fully general because we already know that there are P for which this is not true. This kind of phenomenon is not true. So we want to know whether other than diagonalizability may be a bit too much to assume. So what else can we assume? Okay. So every matrix you cannot reduce by similarity transformation to the diagonal matrix. But there is a more general form to which every matrix can be reduced, and that is called the Jordan canonical form. Now, if you do not know it, I will just recall what it is. So any matrix, like any matrix, P can be reduced to Jordan canonical form. So what is okay, maybe I make the assumptions on P first and then tell what Jordan canonical form is. Assume. Now I will only assume that I will not assume P is diagonalizable. Assume that P has distinct eigenvalues. Let's write the distinct eigenvalues. See, the problem is when all eigenvalues are distinct, it will be diagonalizable. What can happen, the problem we see in linear algebra class is sometimes eigenvalues can have arithmetic multiplicity but not corresponding geometric multiplicity. In other words, it may be it may be a multiplicity root 3, a root of the characteristic polynomial of multiplicity 3, but there may be only 2 independent eigenvectors. That is possible. So what we assume now, okay, so let's write the distinct eigenvalues. I will use the same notation, but I have some distinct eigenvalues, lambda 2, lambda 3 up to some maybe lambda k. But they occur with multiplicities. So they occur with some multiplicities, which I will call M2, M3, Mk. M2, M3, Mk. See, this so far I have not made any assumption. Any matrix P has some number of eigenvalues, some multiplicities, and because it's a transition matrix, 1 is an eigenvalue. Where the assumption comes is that I will assume that this has multiplicity 1. Okay, so this is the assumption. That is, this is a simple eigenvalue. I mean, if you use that word, simple eigenvalue, which means it occurs with multiplicity 1. Okay, and all the other eigenvalues are, and there is more assumption. This is not all the assumption, and I will still assume that all these other eigenvalues are strictly smaller than 1 for all k greater than or equal to 2. This is also an assumption. Okay, so this is also an assumption. So really the assumption part here is that 1, the eigenvalue 1 has multiplicity 1, and all the other eigenvalues are strictly smaller than 1 in absolute value. This is much weaker than assuming diagonalizability and all that. Now, there is no need to assume diagonalizability. Okay, so what is the point of this? And the Jordan canonical, the Jordan decomposition of a matrix tells us, if you have not seen it, this is the conclusion. I will write it in the case that I need. So then this conclusion is what we get. Then P we can write as X.
He had some question, I think. Riddhi?
Yes.
Just a minute. You said already lambda k's are less than 1. So aren't these assumptions same?
No, here it's less than equal to 1.
So but the two assumptions that these two new assumptions are same, right?
This part is the same. This part is the same.
I didn't mean that. See, these already you have lambda k is less than or equal to 1, right?
Yes.
And then you are saying this one occurs only with one multiplicity. So these two are same assumptions.
No. They can be complex. So they can have.
Oh, okay. Sorry.
Yeah.
I got confused. Thank you.
Yeah. No, it's otherwise. So it can be, for example, there can be -1 can be an eigenvalue.
Right. Yeah. So you are not allowing those on the unit circle except 1. Okay.
Exactly. Yeah.
Okay,
so for example, one of the bad matrices I had yesterday. So here, if you look at, there were 2 bad matrices. If you remember, if anybody doesn't remember, ignore this point. There were 2 matrices for which P to the T was not converging in the way I wanted. One was this, where one eigenvalue 1 occurs with multiplicity 2 here. And here is another P, 0, 1, 1, 0. Here, one eigenvalue is 1, one eigenvalue is -1.
Yeah.
So, both are problematic. Both of them violate the assumptions I'm making now. Even if I have eigenvalue I or some other complex number of absolute value 1, there will be trouble.
Thank you very much.
Yeah. So what is the Jordan canonical form saying? That I can write P as X D X inverse. D is no longer going to be diagonal. I will say what it is, where D is block diagonal in this way. Okay. This is Jordan canonical form works like this. You will put the So this eigenvalue has multiplicity 1. So that will occur on the diagonal and nothing else will be there on that row or that column. Okay. But lambda 2 has multiplicity m2. So what I will have here is a block matrix of size m2 cross m2 cross m2, and this I will call j lambda 2 m2. Okay, I will tell you what this matrix is, and then the rest of it will be 0, and then there will be another block which will be j lambda 3 m3, and so on up to all the distinct eigenvalues. By the way, the sum of these multiplicities have to be plus 1 has to be n, because that's the total size of the matrix. So this will go on up to the last block, which is j lambda k mk. Okay, I have scrolled it there. Maybe it's not that visible. And everything else below and above is 0. And what is this j lambda? So I have to tell you what are these j lambdas. J lambda, when I write j lambda super m, what do I mean? It is not quite a diagonal matrix, but it will be an m cross m matrix where lambda is on the diagonal, everything below is 0, but just above there is 1. See, if this ones were not there and it was all just diagonal, this would be a diagonalization. This would become a diagonal matrix. But there is this 1, 1, 1, 1, 1 just above the diagonal, and above that everything is 0. And this is an m cross m matrix. So this is called a Jordan block. So what we are saying is that you can, by a similarity transformation, that is x dx inverse, we can reduce P to this Jordan block form. We have, because 1 is an eigenvalue with multiplicity 1, that Jordan block will be, so you could have written this as J1, 1, but that is same as just a single, when this is a 1 by 1 block, you will just have lambda. So that is a single block of Jordan. So you can also call this a 1 by 1 Jordan block if you like. So that is there. And the rest are some whatever be the block sizes. So this is called a Jordan canonical form. This is the Jordan decomposition. So I do not know if it is usually taught in linear algebra classes, but if not, this is a good motivation to learn about it. So this is still a good form. Every matrix can be reduced to this. Every matrix cannot be reduced to diagonal form, but they can be reduced to this. Now this is already good enough for us. And what is this x? Okay, let's also tell what is x. In general, this x will be a bit complicated what the columns are, but since 1 occurs with so 1 is a simple eigenvalue, so this x will still look like that. The first column of x will be just the eigenvector of, and then there will be other stuff. So earlier when P was diagonalizable, I said all the columns of x are eigenvectors of P. Here they are not necessarily eigenvectors. If the block size is 1, for example, then it will be an eigenvector. If the block size is not 1, they need not be eigenvectors. So, well, okay. So, but the first one is necessarily an eigenvector. And x inverse, similarly, I will write as the first row, whatever it is, I will write as pi 1, pi 2, pi m, pi n. And then whatever junk is there, I'll just put stars there. Okay, so it will look like this. This is the Jordan canonical form of a matrix. From the assumption that 1 has multiplicity 1, we get it in this form. But once we have it, yes.
There is a question, Rahul,
Yes.
regarding Jordan canonical.
Yeah.
Is this the Jordan decomposition of any matrix, or is it particular for the choice of P?
So, yeah, so the only thing special here is that I assume that 1 is an eigenvalue of multiplicity 1, which is why I have here a Jordan block of size 1. Okay. If, for example, if I had written some lambda 1 with multiplicity m1, here this would not be a 1 by 1 block, but this would be an m1 by m1 block, j lambda 1 m1. That's all. That would be the fully general Jordan decomposition, and that's true for any matrix, for any n cross n matrix. This is the only special thing used is that this particular eigenvalue has multiplicity 1.
So this is a proximal map, right?
What is
These are
that?
called proximal map, where it has one top eigenvalue has multiplicity 1.
Oh, okay. Yeah. Okay. So, yeah, I did not know that phrase. So, I will say a condition when, okay, this is an assumption I have made. It is not clear when this assumption is satisfied. I will explain that. I mean,
And
I will
we are
mention that. Huh?
sorry, we are working on in complex numbers for this.
Yeah, so these lambdas can be complex numbers. So although P will be real, when we do this kind of stuff, we will allow complex numbers. Yeah, actually some of this, I mean, but you can reduce it to real case. Okay, these lambdas can be complex.
But
Lambdas
this Jordan form can be in real form. So the Jordan canonical form can be in real.
But lambda can be complex, right?
Yes, here you can have complex, but these can be with cos theta, sin theta, and so on.
Okay. Yeah, right. Yeah, I don't, for me, it doesn't matter if it is complex valued. Okay, so this decomposition can be with complex numbers. But the only thing is now when we take powers, exactly like before, the only thing is P to the power T will be exactly like before, x inverse x will cancel and I'll get x times d raised to the power T x inverse. Now, the question is what happens to d raised to the power T? Okay, d raised to the power T will have, it will be in the block form, 1 will remain. Then we have this j, let me just call it j2. Okay, j2 to the power of T, j3 to the power of T in block form. Okay, and jk to the power of T. What you can check is this converges to 1 and everything else is 0. Only one entry, so it converges exactly to the same sort of thing. The reason is j lambda to the power T converges to 0 if mod lambda is less than 1. Okay, so this is, I'll maybe put it as exercise. It's a very simple exercise. I mean, you can try. Just take power 2 and see what happens. So when you raise this to a high power, the diagonal entries you will see will be lambda to the T, right? And they are going to 0 for sure, with mod lambda is less than 1. But what happens to the off-diagonal entries? They will also get powers of lambda. When you square it, here now we have 1, but when we square j, here you will get lambdas, and when you cube, you will get powers of lambda and so on. So all entries will have powers of lambda, and that will go to 0. So this P to the T matrix will converge to exactly the same as before, x times this matrix with all 1 and 0s, x inverse, and that we already saw is same as pi 1. Now it is same as pi 1 up to pi n dot pi 1 up to pi n. Okay, and clearly pi I is, because they are the limits of non-negative numbers, pi i's are greater than or equal to 0 and summation pi I is equal to 1. So under a more general assumption than diagonalizability, namely this assumption, let's give it a name maybe. So this assumption, so let's call it star star. Okay, so this assumption is quite general and it subsumes the previous case. Okay, so if some P is diagonalizable and 1 is a simple eigenvalue, then the Jordan canonical form will be just the diagonal matrix, and so that this is more general than that one. But the question is, okay, now this is not too bad. You can, if you have a transition matrix at hand, you can check this. You can compute its eigenvalues. You can check if one has multiplicity 1 and whether the other eigenvalues have absolute value less than 1. You can check that, but there is an even neater way to check this, and that is you don't have to actually do a computation like of the eigenvalues to check this, and that is the famous Perron-Frobenius theorem. So I will now state the Perron-Frobenius theorem. So far I have not made any, I have not given you anything unproved. This is one theorem, which I will not prove here, but it is a very important theorem. So you have good motivation to read about it. Okay, the other thing I did not do is, anyway, I wouldn't do is Jordan canonical form. If people don't know that, that also is very much worth learning. So Perron-Frobenius theorem tells us when the assumption star star is satisfied. Okay. Okay, so there are two terms. I will first write the terms and then explain what they are. Okay. So assume that P is, I am bringing a word, irreducible. This is a new word which I have not introduced so far, and aperiodic. Both words I need to explain to you. Then the assumption star star is satisfied. So this was the assumption that 1 is a simple eigenvalue and all other eigenvalues have absolute value less than 1. And hence, once that assumption is satisfied, we have seen that p to the t I comma j converges to pi j for all I comma j as t goes to infinity, where pi 1 up to pi n is the first row of X inverse. Okay, so I will come to what is pi 1, pi 2, pi n. But so if the statement is this, the Perron-Frobenius statement is if P is irreducible and aperiodic, then this assumption is satisfied. And what is irreducible and aperiodic? Okay, so this is very meaningful and very natural in terms of Markov chains. Okay, so what is irreducible? What is aperiodic? Okay, so let's define both of them. Irreducible it means the following, that for any I and j in the state space, there exists a time, okay, such that there exists t greater than equal to 1 or greater than equal to 0 even. Oh no, yeah, it doesn't matter, t greater than equal to 0, such that p to the t I comma j is strictly positive. Okay, what is the meaning of this? It means, so remember p to the t I comma j is that probability that xt is equal to j given that x0 equal to I. Okay, so we are not saying for any particular time. There is some time when this is positive. So what is the meaning of this? Its meaning is, so what if that is not the case? If this is 0 for every I and j, if for some I and j, if this is 0 for all t, what does it mean? It means you can never go to j starting from I. Okay, so this just means that, meaning is that from any state we can go to any other state. Any other state. Okay, any state we can go to any other state, not in one step, in multiple steps, in some number of steps. So when is such a thing not possible? Let's go back to the bad examples of last time. So when P is 1, 0, 0, 1, what does happen? There are two states, 1 and 2. If you start at 1, you will always stay at 1, right? Because from 1, you have probability 1 to stay at 1. So you'll always stay at 1. From 2, you'll always stay at 2. So however much you do, P to the T 1, 2 will never be non-zero. You cannot go from state 1 to state 2 at all, however many steps it takes. So this is a case of reducible. This is reducible, not irreducible. So whenever you have a P which is of the block form, then if P, so when does this fail? If P looks like a block form, if you can write it in a block form, okay, or even one side is 0, okay, even if this is not 0, if this is, it doesn't matter, this doesn't have to be 0, this would be reducible. Because from any of these states, you can never go to any of these states. It's always 0. So this would be reducible. So it's very simple that so this is very natural. In most Markov chains, our states are such that starting from anywhere, you can go to any other place. Okay, so then it would be irreducible. So that is one of the assumptions here. All the chains I told you the other day are irreducible. Okay, we will go back to those examples. And what is the meaning of aperiodic? Aperiodic. What does it mean? Okay, so fix a state I. Actually, what I'm going to say will not depend on which state I fix. Okay, so fix a state I and consider the set of all times when I can be back at I. So that is all those times when I can be back at I. P to the T I comma I is positive. Okay. So this means these are the times when I can actually return to I. Okay. So this set of times, if the GCD of this is 1, and suppose GCD is 1, then we say that P is, okay, we say that I is aperiodic. Okay, if this happens for all I, we say P is aperiodic. Okay, if the GCD is 1, then we say that it is. So if this is true for all I in S, we say P is aperiodic. So let us look at examples. Let's go back to our examples. So first let's do the trivial example. Here what happens, you look at when you can come back to 1. So what are the powers of P when the 1, 1 entry is non-zero? We saw that it happens only at 2, 4, 6, 8, whereas at odd powers this is 0. That means if I look at that set of times when I can return to the P to the T 1, 1 positive, in this example, it is only even numbers. So the GCD is 2. So this is periodic. Okay, so this is periodic. This is periodic. In fact, the period is 2. The GCD is 2. So some chains are periodic and it's a very annoying problem. Okay, so periodicity is just a very irritating problem. So it's best to assume things are periodic, though sometimes it's not. For example, let's look at this kind of situation. Look at the Eigenfest chain. Suppose you start at 0. After one step, you will be at 1. After 2 steps, you will be either at 0 or 2. After 3 steps, you will be at an odd number. So you see that at even times, if you start at 0, at even times, you will be at even numbers. At odd times, you will be at odd numbers, because always you go plus or minus 1. That means the times when you can come back to the starting point has to be an even number. It cannot be an odd number. So this is periodic also. This one is periodic. Okay, let's go over each of these. So this is periodic. So in a way, it's slightly annoying. This is periodic. But, well, what can one do? So this is periodic. So let's look at some other situation. For example, simple random walk on a graph. Okay. So what are the, so take any vertex here. So from 1, what are the times when I can come back? Well, I can go to 2 and then I can come back. I can come back in 2 steps by going to 2 and coming back. I can also go to 2, go to 3 and come back. So I can come back in 2 steps. I can also come back in 3 steps. So that means the GCD will be necessarily 1. And you can check that is true for any of these actually. So it is going to be periodic. Aperiodic. So this is aperiodic. Some simple random walks on some graphs could be periodic. Okay, so for example, simple random walk on a graph like this. This square, if there are 4 vertices, it is periodic, because if you start here at time 0, then at time 1 you will be in one of these 2 places. And at even times you will be in these places, at odd times you will be in these places. So this would be periodic, whereas this one is aperiodic. Okay, and 2-state Markov chain, if alpha beta is strictly between 0 and 1, that is aperiodic. Okay, and so on. So sometimes that can happen. So card shuffling, when I was doing random transpositions, this is aperiodic, because you can, whenever one of the simple ways in which a chain can be aperiodic is if PII is 1. If the diagonal entries are positive, that means you can come back in 1 step. That means the GCD has to be 1. Okay. So anyway, the statement is that if it is irreducible and aperiodic, then our assumptions are satisfied, and these are easy to check in any given situation. So we will get the conclusion that we want.
Sir, there is a question. Is there a probabilistic meaning to aperiodicity?
Yeah, it's exactly that. See, the what is our issue? Okay, so it's a good. Let me explain it in just here. So the question for us, what is the long-term behavior of a Markov chain question? So we start somewhere. Question is, after a very long time, what is the probability I am in various states? Now let's do it on this graph. If you do it on this square graph, suppose I start here. Suppose this is the starting point for me. This square, this point. Then after 1,000 steps, where am I? Now, after 1,000 steps, I don't know anything about this graph, but I know that I have to be in either this or this. Either this or this. After 1,000 steps, I'll be in one of these 2, and certainly not in this or this. But after 1,001 steps, I will be in either this or this, but not in these 2. Right? So in some sense, I have some information, but that's kind of a useless information. I mean, it's a very irritating information. It's just coming from parity. So which is what we want to avoid. So aperiodicity means you forget. So we are not fully forgetting the starting point, because after even number of steps, we will be in these 2. After odd number of steps, we'll be in those 2. In that sense, the memory of the starting point remains. So aperiodicity gets rid of that. Okay. I hope that answers the question. So if there are more questions, we can, of course, certainly on that point, I can explain. So this is what happens with the this. Okay, so always take your Markov chain to be irreducible and aperiodic. Here, let me just make a remark that one can easily convert. So one easy condition for aperiodicity is that P, the diagonal entries are positive for all I. Okay, that's enough to ensure aperiodicity, because this set will contain the number 1 and then the GCD can only be 1. Okay, so that finishes the statement of long-term. This is the main theorem which gives us the long-term behavior of the Markov chain. Any irreducible and aperiodic chain, P to the T ij converges to pi j, forgetting the initial condition, and it will be this pi j. Okay. Now, what I would like to explain further in the remaining, maybe I take 10 minutes. We started at 11:35, so I'll take is okay, I hope. So I will explain what is this pi, and we should compute it for a few examples. So what is this pi? That's what I want to go. What is pi? Okay. So I would like to explain in 2 ways. One is, we saw from the above, from the derivation itself, we saw that first row of X inverse is pi 1, pi 2, pi n. Okay. Okay. But what is the meaning of first row of X inverse? Okay. First column of X, what was the first column of X? It was the eigenvector of P with eigenvalue 1. Okay. What is the first row of X inverse? That also is, it's nothing but, so this is nothing but, this just means that if you write it as a column vector, pi 1 to pi n is an eigenvector. In this case, in our assumptions, it was an eigenvector not of P, but of P star. What is P star? The transpose. Transpose of P. I am not writing Pt because that will confuse with the time t. So I am writing P star, which is usually used for conjugate transpose. P star with eigenvalue 1. With eigenvalue 1. Okay. Now what is it? Why is that? It is simple. So what we got was that P is X D X inverse. Okay. Then P star is, you conjugate everything, so you'll get X star inverse D inverse, D star will be D itself, or okay, let's write D star and then X star, depending, D star need not be D in the Jordan canonical case. So P star is like this. So in other words, P star applied to, okay, something is wrong. So P is XD X inverse or X inverse? XD X inverse. Yeah, so P. Right. So this means that P X star inverse. X star inverse is same as X inverse star. Okay, it's the same, is the same as X inverse star D star. Okay, so this is, with P star. Okay, so this is just a first eigenvector of P star. So this means that the first column of X inverse transpose is the eigenvector of P star with eigenvalue 1. So we get the idea that this pi is nothing but the eigenvector of that transpose of P. In fact, that's easy to see in another way, which is a very important way. So let me explain that other way. Even if you did not follow the derivation, okay, In fact, we can see this, we can see this another way, and this is a useful way. Goes to a very often used idea in mathematics. We can see this in another way. Okay, suppose, so what is this other way? So you may know this idea that if you, so fixed point and iteration, they go hand in hand, right? So let me, so say you take some number, okay? And so let's say you start with x equal to 0 and you define k equals 1. Okay, so we should do the other way. K less than equal to 30, k plus plus. Suppose I make x is cos of x, okay, and I print x. Okay. I just suppose I run this. I just start some. Oh, okay. So mistake. This I should make it numerical. So if I keep applying cosine to, I start with some x. Okay. If I keep applying cosine, then it converges to some number 0.73908, something like that. You start somewhere else. Suppose instead of 0, I started 0.4. Okay, what happens? It is still converging exactly this to the same point. Why is it converging to the same point? I keep applying cosine to it. So what is this number to which it is converging? And we know it's a repeating idea in mathematics that if I keep applying cosine and it converges to something, this number is something to which if I apply cosine once more, it shouldn't change. So if I try to solve cosine of x, cosine of t equal to t, okay, so what will be the solution to cosine of t equal to t? There are many complex solutions, but you see the real solution is 0.739085. And that's what it is converging to. It makes sense, right? If you keep applying cosines, you converge to something. What that something is something for which if you apply one more cosine, it should make no difference. So this idea of iteration and fixed point, the limits of iterations are fixed points, is something that we comes again and again in mathematics, and it cuts both ways, and we can use that. So how do we use that? Suppose we know nothing. We don't know all the mechanism. You didn't listen to what I was saying before. Assume that p to the t I comma j converges to pi j for all I comma j. Suppose I assume that this happens. Then p to the t plus 1 I comma j also converges to pi j. It's just one more time. Instead of t, I have done t plus 1. But what is p to the t plus 1 I comma j? That is, I apply p into p to the t, and then we are taking the I comma j entry. Right? But what is p, this one? This is sum of pik, and then I should take p to the t k comma j. Okay, summed over k in S. And we know that p to the t kj converges to pi j. So this is converging to pik pi, sorry, pik pi, something is wrong. Okay, what did I do wrong? Sorry, I should have done it the other way, maybe. Let me do it the other way. P to the t and p. So this will become p to the t ik and then p kj. So then this p to the t ik converges to pi k. P to the t ik converges to pi k, and p kj, p k j, sum over k. So we get the equation. So what is this telling us? So this is telling us that pi j must be equal to pi k p k j summed over k for all j in S. So if at all p to the t ij converges to pi j, that pi should satisfy this equation. But this is exactly same as, if you write it in vector form, same as p star applied to the column vector pi equal to pi in matrix form. So that's the eigenvalue equation with eigenvalue 1. Eigenvector equation with eigenvalue 1. So this pi will be satisfying these equations. That's what it says. Okay, so maybe I will stop here. So we will do work out this thing in some of the examples and then go a bit more. Okay.
So
Yeah.
there were some questions.
Yeah, sure. We can. So in the here I don't see any questions in the chat. Oh,
No, it is there. Q and A.
oh, sorry, right. That's Q&A. Okay. Yeah. Okay. First question I had answered. So is the Jordan decomposition? It is true for any matrix, but we use this form of P, namely the single eigenvalue. One is a simple eigenvalue that we used in our case. Is there a probabilistic meaning to aperiodicity? This also I answered. Mainly aperiodicity doesn't really give, it's just a very annoying problem. So we try to get rid of it. Okay. How do we know that the pi i's in the first row of inverse of x used for Jordan form is not complex? Okay. So in general, I'm not saying anything about that. But in our situation, when we prove that p to the t ij converges to pi j, then these are positive numbers. So this has to be positive number. Cannot be a complex number or even negative. And since these add up to 1 when I sum over j, these also sum over j will add up to 1. So I am using the, a priori I didn't know what pi j's were. Actually, the Perron-Frobenius theorem tells you that the eigenvectors have positive entries. But in my case, I am just using it post facto, that since it's the limit of positive numbers, it's a positive number. So that's what I am using here. Okay, so next question. What is the significance of not being dependent on the initial state? That means, yeah, so see, if you think of it, after a very long time, what information is there? Okay, so you start from somewhere, you start from, in this random walk, you start from somewhere. After a long time, it shouldn't matter where you started from. Okay, so I mean, this is the forgetting of initial conditions. So it would be very strange if it depends on very precisely how it started. Like, yeah, that's exactly what it means, that the initial state is forgotten and it gets completely mixed up and it will have certain probabilities of being in various places. If it were to retain the initial condition, that would mean something strange. So this is called ergodicity, kind of, yeah, it's related to ergodicity. Yeah. Okay. There is a question. Can we have 0 or 1 in any of the pi 1, pi 2, pi n? Very good question. So I have not yet said it, but when we assume irreducible, they cannot be, they will all be strict positive. So all of them have to be less than 1. So the question is whether these probabilities, some of them can be 0 or 1. If we make this assumption, then all the pi i's will be, in fact, strictly between 0 and 1. I don't know if I'll be able to explain it in the next part, but it can be justified that none of them is 0. So quite simply, I'll explain that. But none of them can be actually 0. Yeah, but there are more general situations where you don't have irreducibility and aperiodicity, in which case some things go away. Yeah. Okay. Are there any other questions on the? Hello?
No, there is no question on YouTube.
Okay.
I just have a
Yes.
comment.
And
Manjunath, you took that eigenvalue 1 and rest all less than 1. So
Yes.
for proximal map, it's known that p to the power n v converges to v1, where
Okay.
v1 is the eigenvector for top eigenvalue. This is known already. So
Yeah. So this is exactly, I mean, so this is
this you showed, but yeah, that's how it is.